we're talking state space. Here's the state space representation. A, B, C, and D are matrices. General, X, U, and Y are vectors. In my course, U and Y will be scalars. But you recall, we had to define our state variables a certain way to come up with these in any particular format. It turns out there's not a unique way to define the state variables. So in this video, we're going to talk about the canonical forms of state space representation. So let's say this is your transfer function. It's pretty general, I think. This would be unique. The A's and B's here would be unique. How to translate that into state space is not unique. Here is one way, which is called the control canonical form. I won't go through this. This would be something you put on a formula sheet. So don't bother memorizing this. But if you had the transfer function, you could come up with the canonical form, the control canonical form of the state space. Similarly, there's something called observer canonical form. Same starting transfer function. Here's the state space representation in observer canonical format. See, in both cases, the D was 0. There's duality between control canonical and observer canonical. So if you had the A, B, and C of one of them, you could get the A, B, and C of the other by these operations. This guy's A would be that guy's transpose of A. This guy's B would be this guy's transpose of C. This guy's C would be this guy's transpose of B. We'll do an example of that in a second. So once you have one, you can get the other format easily. Here's something we'll talk about in later videos. But if you can put the system in control canonical form, it is controllable. If you can put it in observer canonical form, it is observable. We'll talk more about those later. One more canonical format. This is your transfer function. You do partial fractal expansion and express it this way. And then this would be the diagonal canonical format. At least we're going to limit ourselves to these poles are real and simple, meaning not repeated. So once you do the partial fractal expansion, it's easy to put it into diagonal canonical format. See, in diagonal format, the A is diagonal. It's a diagonal matrix. All zeros on the upper and lower triangles means diagonal. If you're rusty on matrices, see my NMAT A course. So let's take an example. Here's a given transfer function. To get it into the format we need to put it into one of the controllable, either controllable or observable canonical format, we need to multiply this out. So we've got a little bit of tedious algebra here. I won't go through this. But that denominator, or this denominator, is this. We multiply it out. So here's what we do. Once we have it in that format, we can match what these B's and A's are, and then go back to our formula sheet and see what the canonical form is. You know, B3 is 5. B2 is 28. There would be an A0 here, but it's 0 in this case because there's no constant. But anyway, go back to that formula sheet. Here's the control canonical form. Here's the observable canonical form. Notice that this matrix is the transpose of this matrix. This matrix is the transpose of that. And this matrix is the transpose of that matrix. So if you had this guy, you can find this guy pretty easy. You want to put it in diagonal canonical form. At least it was good we had it factored like this. We need to do partial fraction expansion. Fortunately, they're simple real poles, so we can use the cover-up method, which is still fairly tedious arithmetic. I won't go through this. Once you calculate these k's, and we get it in this format, it's easy to put it in diagonal form. Here's the diagonal form. P's are the poles, which were, what were the poles? 0, -1, -3, and -4. That's what goes along the diagonal. 0, -1, -3, -4. And these k's come from partial fraction expansion. 2, 1, -3, 5. 2, 1, -3, 5. You just have to make sure these poles in this A matrix are in the same order as the k's are in this B matrix. So those are control canonical forms. We'll use them a little bit later. I don't want to spend too much time on them, but that's what they are. Put them on your formula sheet.